This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2019 AP Calculus exam, free response question AB1 BC1, namely the average value of a function. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. First, I'll provide a little background to this topic, what you need to know before solving average value problems. And then I'll present a little real-world motivation for this concept. Then we'll derive the formula for average value, take a look at the formal definition, and interpret this definition graphically. I'll present a few examples along the way, and we'll see how this concept leads to the mean value theorem for integrals. We often see questions on the AP Calculus exam involving the average value of a function. Now, many of these questions are in the free response section of the exam, and they're in the context of an applied problem. So my objective here is to be able to compute the average value of a function, of course, and to visualize the result and interpret the result. In order to find an average value analytically, I think you need to know antidifferentiation rules and techniques, and the Fundamental Theorem of Calculus. Let's try a little motivation for this concept. Consider a set of numbers or observations, x sub 1, x sub 2, down to x sub n. Now, it's pretty easy to find the arithmetic mean or the sample mean. That's x bar, which is the sum of the numbers divided by n. Now, we have a tendency to call this value the average, but it's really n average. There are lots of different kinds of averages, for example, the median or the mode. But for AP Calculus, we'll call this the average. That is, we'll associate the sample mean with the average. Now, how do we extend this idea to a case in which there are infinitely many numbers or observations? For example, how do we compute the average volume of water in a reservoir over a time interval? There are infinitely many volume measurements possible. So we can't add up all of these observations and divide by n, but here's a graph to illustrate this idea. This figure shows a graph of V, the volume of water in a reservoir over the time interval 0 to 24 hours. It seems reasonable that there is some number, here the average volume, over the time period, maybe near the value V sub average. Now the question is, how do we find that value? Our objective is to find the average value of a function over the interval a to b. So let's try a typical calculus approach. That is, let's find an estimate and then see what happens when we try to find better and better approximations. So we'll start by constructing a regular partition of the interval a to b. And that is, we'll divide the interval a to b into n equal subintervals, each of width delta x, equal to b minus a divided by n. Then select the value x sub I star in each subinterval. Next, find the average of the numbers f of x sub 1 star, f of x sub 2 star, all the way down the line to f of x sub n star. So, for example, if f represented the volume of the reservoir and n was equal to 48, then we'd take the volume reading every half hour and find the average of those values. Now, because delta x is equal to b minus a divided by n, we can solve this expression for n. And let's use this expression for n to rewrite the expression for average value. Here's the average value of the n numbers, with the expression for n in terms of b and a and delta x in the denominator. First, I'll rewrite this fraction And then I'll distribute the term delta x. And finally, I'll write this expression more compactly using summation notation. Now you should probably recognize this expression as a Riemann sum. And we know that the limiting value of a Riemann sum is the definition of a definite integral. So if we want a better approximation of the average value, it seems reasonable to take more numbers, or let n increase. And as n goes to infinity, the limit of this Riemann sum is a definite integral from a to b of f of x dx. So this gives us the definition of the average value of a function f over the interval a to b. It is 1 divided by b minus a times the definite integral from a to b of f of x dx. Now, if f of x is greater than or equal to 0, here's an interpretation. The average value, or the average height of the graph, is the area under the curve from a to b divided by the width of the interval. Let's try a quick example. Find the average value of the function f on the interval 0 to 3. Now, just to connect this to our definition, the interval here is of course 0 to 3. So a equals 0 and b equals 3. Using the definition of the average value, we need to find 1/3 times the value of this definite integral. So I used some basic antidifferentiation rules and the Fundamental Theorem of Calculus to evaluate the definite integral. And I found that the average value over the interval 0 to 3 is 3. Here's a graph of the function f and the horizontal line y equal the average value. Since f of x is greater than or equal to 0 on the interval 0 to 3, you can kind of see that the average value is the average height of the graph. And the area of the region bounded by the graph of f, the x-axis, and the lines x equal a and x equal b, is the same as the area of the rectangle with height equal to the average value and width b minus a. Here's an example for you to consider that involves a trigonometric function. So suppose the function f is given by f of x is equal to 2 plus the cosine of x. Find the average value of the function f over this interval, minus pi over 6 to 5 pi over 6. And carefully sketch a graph to illustrate this result. Now it seems reasonable to ask if there is some point in the interval where the value of the function is exactly equal to its average value. If you peek back at the opening reservoir example, it appears that there are at least 4 places or times at which this occurs. So it turns out that for a continuous function, there is at least one number c at which the value of the function is exactly equal to the average value of the function. That is, f of c is equal to f sub average. This leads to the mean value theorem for integrals. It says that if f is continuous on the interval a to b, then there exists a number c in the interval a to b such that f of c is equal to the average value, 1 divided by b minus a, times the definite integral from a to b of f of x dx. Or, if we multiply both sides of that expression by b minus a, the definite integral from a to b of f of x dx is equal to f of c times b minus a. This theorem seems pretty reasonable, especially in light of the graphs we've been looking at. But it can be proved using the mean value theorem and the Fundamental Theorem of Calculus. And here's one more geometric illustration of this result. For positive functions f, there is a number c such that the rectangle with base a to b and height f of c has the exact same area as the area under the graph of f from a to b. So you can always sort of chop off that top of the two-dimensional mountain at a certain height and use it to fill in the valleys so that the mountaintop becomes completely flat. Now, truthfully, this figure doesn't look much different from the previous figures. The difference here is that we are guaranteed that there is at least one number c in the interval a to b, so that f of c is equal to the average value of the function. Let's try another example. Here's a function f that's a polynomial. Well, a quadratic. The function is certainly continuous on the interval 0 to 4. Therefore, the mean value theorem for integrals says that there is a number c in the interval 0 to 4 such that the definite integral from 0 to 4 of f of x dx is equal to f of c times 4 minus 0. Let's use some technology to find this value of c and to illustrate the result. First, I defined the function f, and then I found the value of the definite integral. I used the solve function to find the value of c guaranteed to exist. Well, it turns out that there are two values here that satisfy this equation, and these values are given symbolically. So I have to think a little bit about their numerical approximations, and only the first value here lies in the interval 0 to 4. I want to be able to use that value of c without writing it in again, without typing it into the calculator. So here's a neat trick. I used the zeros function to find the same values, but placed them in a list, and I can reference the values in that list. So here I assigned the first value in the list to the variable c. And here's a graph on the TI-Nspire to illustrate this result. The shaded region represents the definite integral of f of x from 0 to 4. And the horizontal green line is drawn at the value f of c. And here's one more example for you to consider. A cup of tea with temperature 180 degrees Fahrenheit is placed in a room with temperature 70 degrees. The temperature of the tea after t minutes is given by this function capital T. Find the average temperature of the tea during the first half hour, and carefully sketch a graph to illustrate this result. I hope this video provides some insight into the derivation of the formula for average value of a function, the geometric interpretation, and a few AP Calculus type problems. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.